Okay. So for the second part today, we will discuss about the shear and moment diagram. Okay, shear and moment diagram. So basically, what you have learned up until now is to find out about the internal force and internal moment which is happening at one particular point. Okay, only at one particular point. For example, in this problem, we are asked to find out the internal force and moment at point B only. Okay, and for this particular problem, we are asked to find out the internal force and moment at point C only. Okay, so in your homework as well, there you are only asked to find out for the internal force and internal moment at one particular point only. And the next thing that we want to learn right now is how to find out the internal force and internal moment, but for the whole beam. For the whole beam. Yeah. Yeah. It's slightly different. The way to do it is slightly different because if we just keep using the previous method, okay, it means that if we want to find out the shear force and the internal moment for the whole beam, okay, we have to do a cutting here, 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 okay. There is a lot of cut there, okay, because we if we want to find out for the internal force and moment for the whole beam, it means that the point representation there, it's a lot. Okay, so at every point there, we have to do cutting. And at every point there, we have to do cutting. So it's quite impossible for us to do it the same way as we do it before. Okay, so we cannot just cut it at every point like that. No, we can't. Okay, but how to do it in a simpler way? Okay, the method that we still do is the method that we will use is still cutting method. Okay, we will just cut it at certain location, but at that particular cutting, what we find out is not just the value of the internal force and moment at particular point, but the value of the internal force and moment at certain region. For example, if I do the cutting here, I will try to find out the internal force and moment at this particular region. If I do the cutting here, I will try to find out the internal force and moment at this particular region. And lastly, if I do the cutting here, I will find out the internal force and moment at this particular region. Okay. So what we find out, where we try to find out whenever we do cutting, is not the exact value of the internal force and moment at particular point, directly at that particular point, but the equation. What we want to try to find out is the equation which is representing the shear force value at this region, moment value at this region, and normal force value at this region. The same when we do this particular cutting, what we try to find out is the equation which is representing the normal force value at this region, shear force value at this region, and internal moment at this region, like that. So when we cut, we will not getting exactly a certain value like that, but what we will get is an equation. What we try to get is an equation which representing the value of internal force, internal moment at certain region. Okay. Ini saya coba ulangi konsepnya ya dalam bahasa Indonesia. Jadi kalau misalkan yang kita ingin coba cari sekarang, ini agak sedikit berbeda dengan yang sudah kita pelajari sebelumnya. Yang kita sudah pelajari sebelumnya itu hanyalah gaya dalam, dan mencari gaya dalam dan momen dalam pada titik tertentu saja. Oke, di PR kalian, kemudian di latihan-latihan soal sebelumnya, itu hanya mencari gaya dalam di titik gaya dan momen dalam di titik tertentu saja. Nah, yang sekarang kita ingin cari adalah gaya dan momen dalam diagram gaya dalam dan diagram momen dalam. Diagram gaya dalam dan diagram momen dalam itu merepresentasikan gaya dalam dan momen dalam yang terjadi pada keseluruhan bagian ini. Pada keseluruhan BIM. Oke? Nah, metode yang kita gunakan akan mirip dengan yang sebelumnya, masih cutting, masih pakai dengan cara cutting, tetapi kita cuttingnya tidak pada semua titik ya, tidak, tetapi hanya pada region-region tertentu saja. Misalkan cutting pertama pada region pertama, region A ya, itu dari X1 sama dengan 0 sampai X1 sama dengan A. Kemudian cutting kedua itu pada region B, itu dari X2 sama dengan A sampai X2 sama dengan B. Kemudian cutting yang ketiga itu pada region ketiga ya, itu dari X3 sama dengan X3 sama dengan B sampai X3 sama dengan L, seperti itu. Oke, nah masing-masing cutting nanti itu akan merepresentasikan distribusi gaya dalam dan juga momen dalam pada area, pada region tersebut. Seperti itu. Ya. Jadi nanti pada cutting yang pertama itu persamaan gaya geser dalam, lalu persamaan gaya normal dalam, persamaan momen dalam, ini akan berlaku untuk X1 sampai A, seperti itu. Ya. Kemudian ini yang region pertama ya, potongan pertama. Kemudian untuk yang potongan kedua itu kita juga akan mendapatkan sebenarnya normal, kayak normalnya di sini tidak diperlukan karena tidak ada horizontal, gaya arah horizontalnya. Kita akan dapat V dan M. Untuk X2 lebih besar dari A, lebih kecil dari B, seperti itu. Kemudian yang ketiga, potongan ketiga. Oke, potongan ketiga untuk mendapatkan V dan M untuk X3 dari B sampai L. Seperti itu. Jadi begini ya, logika berpikirnya seperti itu. Nah, intinya adalah kita melakukan section-section di sana. Nah, sebagai contoh, di section pertama tadi, so for example, in the first section, okay, our free body diagram will be like this. Okay, just assume that we already solved for all the external forces. Okay, we have AY here. Assume that we have the value of AY, and W is distributed force. Okay, like that. And we try to find out for the internal forces and moment, like this. But the main difference here, the distance from the left side to the cutting is not a certain value anymore like before, but this one is invariable. In this case, is X1. So X1 is the distance from the cutting to the left edge A, at point A, like that. Okay, so later, our X value and our M value will be in X1. Like that, will be in X1. So like later, V here, it will be in terms of X1, and M will be in terms of X1 as well. Okay. Then in the second cut, okay, for example, we have W until here. Yeah, W until here. Then this is the second cut. We have AY, W, then this one is X2. the distance from the left edge to the cut is x2. Okay, we have this one, v1 m1, v2 m2, like that. Okay, so later v2 and m2 will be in terms of x2. Like this. So what we get in every section is not just the value of a particular point, but an equation which representing a certain region. That's the difference between finding shear and moment diagram in comparison to what we did before to find out the internal force and moment at one particular point. Okay. Until this particular, anyone want to ask question? I believe most of you are still a bit confused about it. Okay, but later I will discuss with the equation and with several problem example in order to make it clearer for you guys. Okay, then I will continue a bit. After we try to solve it for these three regions, okay, this is what we will get. Okay, for the first region, from here to here, okay, we will use this equation for v and m as well. Okay, so for v, this is what we will get from the first region, and this is what we will get for the first region in the moment, internal moment. Yeah. Okay, for the second region is from this particular point till this particular point. Okay, and the equation that we will get from the second region is this. Okay, this is for the internal force, and this is the second region, the equation for the second region for the internal moment. And for the last region, the third region, is from this till the end. Okay, we have the third equation, v3 and m3 in terms of x3, and this is what we will get for the third region. That's the representation of the equation, and this is what we will get for the third region for the moment, like that. So basically, this is the shear and moment diagram that you have to find out. Okay, so later, if you are asked to find out the shear and moment diagram, roughly this is the things that you have to find out. But the curve, the diagram will depend on the system itself, like that. Okay, so what I try to do here is just to give you like some kind of a broad view on the problem. Okay, so when we have a so when we have a problem and you are asked to find out the shear and moment diagram, okay, this is roughly the things that you have to do. You do the cutting, but the cutting there will represent a certain region. Okay, in this case we will have a 3 region. Okay, and then After that, you have to draw the shear and moment diagram based on the equation that you get in each section, like that. Okay, wait a minute. Okay, sorry for the delay. Then there are several things that you need to know in our shear and moment diagram. So basically, here I want to give you guys a broad view on the relation between the shear force, the distributed force W, shear force, and moment. Okay, in order to you to get those relation, okay, please take a look at this problem. So basically, we have a beam which under distributed load like this W, okay, which is in a certain function in terms of x like that, okay, and then we want to find out about the relation between the distributed force W with the shear force P. Okay, in order to do so, I try to create a cut here, but the cut is only covering small element here. Okay, only covering a small element here. So this element only. Okay, and if I try to take a look at this element, okay, this is all the internal forces and internal moment which will be happening at that particular small element. Okay, on the left side of the cut, we will have a moment phi, moment, internal moment, and internal shear force. At the right side of the cut, because there is a W, distributed W at the distance delta x here, okay, there will be, okay, internal shear force plus dV. dV is the delta internal shear force. So phi plus dV there on the right side. And on the right side as well, the moment will be slightly different from the left side because of a W here. So there will be M plus dm, where dm is the delta internal moment. M is the internal moment. Okay. After we find out about the free body diagram of the cut of that particular small element, now I want you to try to implement the sigma Fy equal to 0. If we use sigma Fy equal to 0 in this particular free body diagram, what will you get? Okay, you can see there that there will be phi going up, positive is going up in this case, minus phi plus dv, this one, because it's going downwards, minus. Then we have w multiplied by dx going downwards as well, minus. So w multiplied by dx going downwards, it's supposed to be equal to 0. Okay. If we try to calculate that, so phi minus dv here will be 0. Okay, it will cancel each other. Then what we have left is minus dv minus w dx equal to 0. Okay, if I rearrange the terms, I will get this. W is equal to minus dv per dx, this one. And this one is actually showing us the relation between internal shear force at location x, okay, the function of the internal shear force with the function of the internal of the distributed force. So there is a relation between distributed force and the internal shear force. Okay, next. After that, if we try to do a sigma moment, okay, if we try to do sigma moment, for example, I will try to do sigma moment on the right edge here. Okay, sigma moment at the right edge there, equal to 0. Okay, what I will get there is if we assume that clockwise is positive, what I will get there is moment m minus m plus dm. Okay, then plus v multiplied by dx. Okay, and then minus clockwise is counterclockwise, w multiplied by dx. Okay, multiply by dx over 2, because the length is dx over 2. Okay, this one is equal to 0. Okay, if later you can solve this, okay, if later you can solve this, okay, this is the relation that you will get. Sorry, not this one. This is the relation that you will get. Okay, v is equal to dm per dx. Okay, let's try. Okay, m there will be canceling each other. So what we will get here will be negative dm plus v multiplied by dx. Okay, minus w dx over 2, and this one will be equal to 0. Okay, if you take a look at this part is we have a w multiplied by dx multiplied by dx over 2. Okay, dx is small because the element is very small, and if we multiply dx with dx, it will be very, very small. So this particular part will be negligible. Okay, so we left with this. That's why there we have minus dm plus v dx equal to 0. Okay, so what we will have is v is equal to dm per dx. Okay, so this is our relation between shear force and internal shear force and internal moment. So the differentiation of the internal moment over x will resulting in internal shear force. Okay, so basically this is the relation that you need to know, and if we combine both together, okay, we will find out the relation between moment and the distributed force, which is this one. The second derivative of the moment over x, okay, will be equal to minus w. Yep. So this is the relation that we normally have for distributed force, shear force, internal shear force, and internal moment. Okay. In your calculation later to find out for the internal moment and internal shear force, most of the time we don't have to use this, but we can use this in order to check whether our equation is correct or not based on the relation between one and each other. Like that. Jadi secara garis besar ya, ini adalah hubungan antara distributed force dan juga internal shear force pakai persamaan ini ya. Kemudian hubungan antara shear force dengan internal shear force dan internal moment pakai persamaan ini, dan juga hubungan antara internal moment dan juga distributed force pakai persamaan yang terakhir. Oke, untuk penurunannya bagaimana tadi saya sudah jelaskan. Yang ini kita pakai sigma Fg dari elemen kecil ini. Yang ini kita pakai sigma moment dari elemen kecil tadi. Oke, penggabungan dari keduanya akan mendapatkan yang terakhir. Nah, biasanya tiga persamaan ini itu cenderungnya tidak akan kita gunakan pada saat perhitungan internal force dan juga internal moment diagram. Pada saat mencari diagram gaya dalam, diagram momen dalam itu biasanya ini tidak akan digunakan. Cenderungnya tidak digunakan. Tetapi ini bisa kita gunakan, ketiga persamaan ini bisa kita gunakan untuk mengecek apakah diagram gaya dalam, diagram momen dalam yang kita sudah dapatkan itu sudah oke atau belum. Dari relasi antara distributed force, internal shear force, dan juga internal moment. Seperti itu. Oke. Ini adalah penurunannya. Silahkan jika ada pertanyaan, walaupun mungkin sebagian dari kalian agak sedikit bingung terkait dengan ini ya, tetapi ini sebenarnya saya cukup hanya untuk berikan saja. Kegunaannya nantinya itu hanya untuk pengecekan sebenarnya. Lebih ke arah pengecekan. Seperti itu. Silahkan jika ada pertanyaan. If there is no question, then I will continue with a problem example. Okay, let's start with the problem example. This one is one of the problem example. In this case, we will have a tree. Sorry, we will have a tree section. Okay, in this case, we will have a tree section there. But I'm not so sure whether it will be, we will have enough time to finish this or not. I think I will start with a very simple problem. Okay, a problem which is much simpler than this one. This one is having a tree section, and we only have 20 minutes to solve this. Okay, so I'm afraid that we won't have enough time to solve that. Okay, I think I will start the problem example. Some of the other problem example we will discuss it tomorrow. So for tomorrow, I will give several problem example on how to calculate for the internal force diagram and internal moment diagram. Okay. For today, I will just give a several presentation on the those example. Okay. This is one of the simplest one. We have a beam which is supported like this. On FA, there is a pin joint, and at B, there is a roller joint, and there is a force. There is a force which is happening exactly in the middle. Okay. For example, the length of the beam is 2 meters, and the force here, P, is equal to 10 Newton. Okay, and the force is happening exactly in the middle of the beam, so it's 1 meter. Okay, the first thing that you're supposed to do, as usual, is to solve for the external forces. To solve for the external forces, so we have to solve for the external forces first. At A here we have AY. At B here we have PY. Sorry, A here we have AY and AX. And we have one P equal to 10 Newton. we can solve for ax, ay, and by using sigma fx equal to 0. In this case, what we will get is ax is equal to 0. And we can solve as well using sigma moment at a equal to 0 to get for by. Okay. In this case, what we will get is 10 Newton P multiplied by 1 meter minus Py multiplied by 2 meter is equal to 0. So our Py will be equal to 10 Newton divided by 2. Yeah, 10 Newton divided by 2, so it's 5 Newton. And then lastly, we use sigma Fy equal to 0. What we will get here is Ay plus By minus 10 Newton is equal to 0. By here we know is the value is 5 Newton. So we will get the value of Ay is equal to 10 Newton minus 5 Newton from By. So Ay is equal to 5 Newton. Ay is 5 Newton. Ax is 0, Ay is 5 Newton, and By is 5 Newton. So we know exactly, we know now that all the external forces. The next thing that we're supposed to do is to perform a cut in order to find out the equation at a certain location, like at a certain region. Sorry. I think I will try to point out somebody here to help me. Naila. Hello, Naila.
Yes, hello, sir.
Okay, Naila. What do you think? Where are we supposed to do the cut here, Naila, in order to find out for the internal force diagram and internal moment diagram?
Can we cut it through the P?
P? No, it will be too difficult because when we cut, right, as I told you before, we have to cut to represent the equation at certain region, and those region must be continuous. Continuous is like what? For example, like this one, the first region, I put it there because it's because there is a distributed force W happening there at the region 1 from this point to this point. Okay, and the things that are happening there is only W, so it's continuous. Okay, the region 2, I cut it here in the middle between this point and this point. Okay, and you can see there between this point and this point, there is nothing there. Okay, there is no force there. So if there is no force, most likely it will be continuous. The equation will be continuous. So I will put it there. And lastly, from this point to this point, okay, there is nothing there as well. And the third region, with this region, there is nothing there between P and the support there. There is nothing there. So most likely it will be continuous. So the first thing that we're supposed to do before we do the cutting is we have to determine how many cuts that we need for this particular beam, like that, in order to create a continuous equation for a certain region. In this case, Naila, what do you think, Naila? Where we supposed to put the cut there? How many cuts that we need?
I think we need 2 cuts.
Yes, correct.
One
We need
next
2
to
cuts.
A and one next to B.
Yep. So like this, right? You mean this is the first cut and this is the second cut, right? So
yes, exactly.
The first cut will represent this particular region, and the second cut will represent this particular region, right, Nela?
Yes, sir.
Okay, good. Now, after we determine the number of cuts that we need and where we're supposed to cut it, then we have to draw the free body diagram of that particular cut. Okay, now let's try to draw the free body diagram of that particular cut. Okay, so this is our free body diagram. Okay, so this is the first cut. Okay, you can see there what we have there, Nela. So this is what I try to get here. So that's the section that I try to solve there. Okay, what we have in that particular cut, Nela.
I'm sorry, sir. I'm still a bit confused.
What forces that we have there? Can you help me to represent all the forces which is happening at this particular cut? This one?
Okay, I think it's AX, AY.
AX is 0, so we don't have to draw it. Okay, so what else beside AX?
I think it's AY.
Y, we have 5 Newton. Okay, what else? Oh, sorry, I think I made a mistake. I will redraw it here. This is the first cut. Okay, we have 5 Newton here. What else besides 5 Newton? That's all, right? For the external forces, that's all, right?
Yes, for the external forces, it's only AY.
Now is the internal. For the internal, what we have there?
I think we need the shear force.
Shear force, V. So it's going downwards because it's positive, right? Clockwise, positive. What else?
Yes. And do we need the normal force too, sir?
What do you think? Remember here, AX is 0, right?
Oh, okay, okay. So we don't need the normal force.
Yeah, we don't need the normal force. What else?
I think we need the moment.
Moment, correct. So it's like this, right? Counterclockwise, positive, in order to make the beam smile, right?
Yes.
Okay, so that's it, right? And the distance there, okay, the distance from the left side to the cut, it's supposed to be, we name it as x1. Okay, we name it as x1. Okay, or if you don't want to put it as x1, yeah, it's okay. Just put it as x1. We name it as x1. Okay, instead of certain value, we name it as x1. Now, if we want to try to solve for phi, then we have to use we have to use sigma fy equal to 0, right? In order to solve for phi, correct, right, Naila?
Yes, sir.
What we have there?
Then we would have 5N minus the shear force.
Okay, right.
Equals to
5
0.
Newton minus phi equal to 0. So phi is equal to
5 Newton.
5 Newton. Although there is nothing there, there is no equation there. It's constant. It means it's still okay because the equation here is constant. So the value of phi will be constant 5 Newton from the left edge until this particular point, until P. Okay, for the first region, the value of phi will be constant 5 Newton. Okay, now next one, in order to find out for M, we can use sigma moment, right? You want to use sigma moment at the left edge or the right edge? Nela.
I think the left edge would be okay, sir.
So sigma moment at A, okay, equal to 0. And in this case, what we will have here?
We would have the shear force times x1.
Okay, times shear force, and we know the value of shear force. Okay, remember. So it's supposed to be 5 Newton multiplied by x1. Okay, I think I will not use this one because it's too complicated. 5 Newton multiplied by x1. What else?
and minus the moment.
Minus m equal to 0. So we now have an equation. M is equal to what?
5 times x1.
5x1. Okay, that's our first free body diagram for our first cut. If we now take a look at the second cut, this one. Okay, let's draw the second cut. Okay, slightly longer. And here we have 10 Newton, P equal to 10 Newton. And there we have 5 Newton. Okay, this is our second cut now, Nela. Correct, right? All those are all the external forces, right, Nela?
Yes, sir.
How about the internal forces? What we have there? What will have there?
I think it's the same as the first section. We have the shear and the moment.
And the direction is the same as well, correct? Okay,
Yes.
we have P and M. Now, the same as before, I want you to solve for phi using sigma Fy equal to 0. Okay, what will we have there?
I think it's just 5 minus 10 plus
10 minus
5
P.
minus 10 minus V
Yeah,
equals
correct,
to 0.
equal to 0. So our phi here will be equal to what?
5 newtons, sir.
Are you sure 5? Are you sure it's 5? Positive or negative? Don't forget the sign.
I think it's negative, sir.
Negative.
Minus 5.
Minus 5 Newton. Please don't forget about the sign, because if positive and negative, it will be very different. Okay, now, in order to find the M, internal moment, we have to use sigma moment, right? Equal to 0. What will we have there in this particular equation? Okay, then. As usual, just use the left edge, okay? Sigma moment at A equal to 0.
I think it's 10 Newton times
1 meter, right?
oh yes, 1 meter.
Meter, and then?
Plus the...
Okay, one more thing. I forgot to add. The distance here is supposed to be x2. Okay, x1 here is between 0 to 1 meter. x2 is between 1 meter to 2 meter. Right. Sorry, it's not like this. Until the cut, it's x2. So 10 Newton multiplied by 1 meter. And what else do we have there?
And then we add the shear force times x2.
Okay.
So
this
it's
one is
minus
plus phi multiplied by x2, correct? But remember, phi here is minus 5 Newton, right?
Yes, sir. So it's
So
just
here,
minus 5 times x2.
Yeah, correct. Minus 5 times x2. And what else?
And then minus m equals
M
to 0.
Equal to 0. So here, what we will have is m equal to, what is this? 10? 10 minus 5x2, right? Correct.
Yes, sir.
Okay, now the next thing that we're supposed to do, actually, this is all the equations that you need. You already solved for the phi. We already solved for m for the first region. Okay, we already solved for phi for the second region. We already solved for the moment for the second region as well. And we only have 2 regions. So we can draw for the shear force diagram and moment diagram. Okay. For the shear force diagram. So let's try to draw for the shear force diagram. This is our shear force diagram. Okay, from x equal to 0 until x equal to 1 meters, what is the value of V, Nela?
Sorry, can you repeat the question again, sir?
Yeah, from x equal to 0 until x equal to 1 meter, what is the value of V? Shear force. What is the value of shear force? You already calculated.
Oh, is it from the first section?
Yes, from the first section. From the first section. 5 Newton, right?
Yes, sir.
And it's supposed to be constant, so it's supposed to be like this. 5 Newton. Okay, next one. Still V, still the shear force, but now from the x equal to 1 meter to x equal to 2 meters. What is the value of shear force V?
It's -5, sir.
Yep, correct. Here in the second section, right? -5. So this is -5 Newton. Okay, and there is a jump here, 10 Newton, at the location of the force, 10 Newton there. Okay, so this is our internal shear force diagram. Okay, this one is 0, this one is 1 meter, this one is 2 meter. Okay, now let's draw for this one is shear force V. Let's draw for the moment diagram. Okay, this one is the moment diagram. One meter, 2 meter, this one is 0, this one is moment. Okay, in order to draw for the moment diagram, we already know the equations, right, Nela?
Yes, sir.
Okay, can you find out the value of moment at x equal to 0, Nela?
Is it just x equals to 0?
Yeah, x equal to 0. It's actually simple. This one is x, right? You just multiply there, right?
Oh, so it's gonna be 0.
0, correct. The value of the moment at x equal to 0 will be 0. Yeah, m at x equal to 0, okay, it will be equal to 0 because this one. And at x equal to 1 meter, it will be, what is the value of moment at x equal to 1 meter?
It will be 5, sir.
5, correct. 5 Newton meter. Okay, you actually can use the first equation or the second equation for the moment. If you use the second equation and you put x equal to 1 meter there, the results will be the same. The moment will be 5 Newton meters, correct, right?
Yes, sir.
Yeah. So we have 0 here and we have 5 here. 5 Newton meter. So this is our graph for the first region. And now for the second region, we already know the moment at x equal to 1 meter is 5 Newton meter. Okay. Now the moment at the x equal to 2 meters, what is the value of that? You have to use the first equation or the second equation in this case, Nela.
I think you can use the second equation.
Second equation, because second equation cover from 1 meters to 2 meters, right? First equation only covers from 0 to 1 meters. So at 2 meters, we have to use the second equation. Okay, now try to put x equal to 2 meters there at the second equation. What is the value there?
I think it's just 0, sir.
Correct, 0. Okay, because we just used this equation, right? 10 minus 5 multiplied by 2. 5 multiplied by 2 is 10, so 0. So our moment there will be 0 as well here. So this is our, and this one will be linear. Okay, and this is our internal moment diagram. Constant going up from 0 to 1 meters, and constant going down, not constant, it's linear going up from 0 to 1 meter, and linearly going down from 1 meters to 2 meters. Okay, do you get it, Naila?
Yes, sir, I think I understand.
And now, in this case, after you guys find out the internal moment diagram and internal shear force diagram, okay, now we know the value of all the internal shear force and all the internal moment at every location. For example, if I want to find out at x equal to 0.5 meters, what is the value of shear force, internal shear force, and what is the value of the internal moment, then I can just do it this way. Okay, maybe this one is misspelled, right? It's supposed to be slightly going to the right. Yep. So this is our value at 0.5 meters, and this is our value at 0.5 meters. So at 0. Or you can just use the equation here for the moment. So at 0.5 meters, x equal to 0.5 meters, is we supposed to use the first equation of moment, then we can use this one. So it's supposed to be 2.5 Newton meters, like that. Okay, so basically, after you find out for the diagram, you can find out all the other points value, all the other location value for the internal force and internal moment. Okay, because we already have the equation like that. Okay, you get it, Naila?
I think I understand, sir.
Okay. For all of you guys, if you are still confused about this, don't worry about it. Tomorrow I will still continue about this and to discuss several other problem example in order to give you guys idea on how to get the internal force and internal moment diagram like this one. Okay, this one is one of the simplest case, so I will give it to you guys today. So tomorrow we will discuss for more complicated problem. Okay, I think that's all for today because it's already 2 minutes before noon. Okay, I think that's all. Thank you very much for listening, and see you guys tomorrow. Okay.
Thank you, sir.
Yeah, thank you. Bye.
Thank you, sir.
Yep.
Thank you, sir.
Thank you.